Hello students, good day. I hope all of you are well and in good spirits. In the previous class, we discussed that during its life cycle, a process can be in different states, including running, ready, and waiting. When a process is in the running state, it means that it is currently being executed in the processor. If it is in the ready state, it means that the process is ready to get executed by the processor, but meanwhile the processor is working with some other process. While if the process is in the waiting state, it means that the process is waiting for an IO operation to complete. When a particular process is running in the processor, it is a possibility that in the meanwhile multiple other processes they may be waiting or they may be ready in the ready state, which means that they are ready to get executed and they are just waiting for this process to complete its time slice. When this time slice expires, the operating system takes out the running process from the processor and puts it into the ready queue. In the ready queue, we have multiple processes which are ready to get executed in the processor, and the operating system selects one of those processes and pass it on to the processor for execution. This selection is based on a particular criteria that we will talk about after a while. For now, we are only concerned about that what happens when one process running in the processor it gets out from the processor and some other process gets in. So this shifting of process or switching the process from the running state to the ready state and from the ready state to the running state, it has some particular dimensions or some different characteristics associated with it. We call it the context switching process. When a process is taken out from the processor, the whole state of this process, like the instruction it is working on, the values of the registers, the values of the stack, the next instruction to be executed, and all the important information that is associated with this process, they are stored somewhere. So this is a process of storing something, and definitely once this process will get the CPU time again, maybe after 10 seconds, maybe after 20 seconds, but whenever this process will get the CPU time again, all of this state that we are storing right now, they will be restored back onto the processor. So we know that processor has some registers, it has and processes, they have instruction numbers, the next instruction to execute. We have stack values that store the return address of different functions and their calling parameters and return values and all of the stuff associated with the process. Along with it, we have a list of open files, some data is being read. So there are several things that are going on in parallel when a process is in the running state or it's being executed. So when context switch happens, we take out this process out of the processor. We have to store all of the states of everything that is associated with the process. And once this process will get the CPU time one more time, like maybe after 10 seconds, 1 minute, or whenever, all of this state has to be restored back onto the processor to continue the execution from where we left earlier. So you can see that we have to store something when we are taking out a process from the processor or shifting it from the running state to the ready state. In the meanwhile, we have to restore some data when we are shifting the process from the ready state to the running state. So this was about one process, but what if we have two processes? So the same thing will happen naturally. When we have process 1 in the processor and we are taking it out, so we will store the whole state of this process, and we will load the state of process 2 on the processor. So this storage or storing the state of the of the process that is going out and storing the state of the process that is coming in, we call it the switching of the context or the context switching. This is important so that CPU or the processor, it can start or it can continue the execution of this process where at the very point where it left earlier. So this context switching process is quite important, and it is one of the key pillars to support the running of multiple processes in parallel in a system that has a single CPU. So this switching of context is a very important, or probably the key feature of systems or operating systems that support multitasking or running of multiple processes simultaneously, or not simultaneously but in parallel or concurrent. Usually this whole process, as you may have figured out, that this whole process is quite computationally expensive. So the storage of the whole state and then restoring it back, it may take some important time. So this is quite something that is not desired to be done quite often. So we have to select the CPU time slice large enough so that we are not doing this context switching so often. On the other hand, we have another trade-off that the longer the CPU time slice is, we will get less responsiveness from the operating system for the execution of concurrent processes. So this is again a trade-off that has to be considered when we are designing an operating system and to optimize the performance of multitasking, as well as to optimize the performance of multiple processes running in parallel. Here we have a list of activities that are carried out when we perform this context switch. So first of all, the operating system saves the value of the program counter, registers, and stack pointer associated with this process that is going to be taken out from the processor. Then it modifies the state of this process in its process control block. We will discuss it in a couple of minutes what it is. And it modifies the state from the running to the ready or block state based on for what reason we are having this context switch. And then it modifies various times for the accounting purposes related to different processes, so we can have a log of the processes and how they actually ran. Then it selects a particular process from the ready queue. This selection is the job of a scheduler, and we will talk about this scheduler in the next module. Then after selection of a process, it puts it into the processor and updates the various fields in the PCB, like from ready to running, and all the things that we stored earlier, including the program counter, registers, stack pointers, memory addresses. So everything that we stored earlier, it is loaded back onto your processor so that the execution can restart or restore from the very moment from where we left it earlier. So in this way, the process may not be actually aware that it was rescheduled, or it got taken out of the processor and now it is going back. So for the process, it is the same thing, that for some while the execution was halted, but actually it was CPU which is giving time to some other process. By the list of activities and the extensivity of this operation, you can see that it's a costly operation. So we have to select this time quite wisely. This is a trade-off between if it is a large value, then only a few processes will be able to do this context switching. So it will be light with respect to the context switching, and only some time will be wasted in this process. While on the other hand, uh, if we will have a large value of this context switch, then the processes will feel that they are not, the operating system or the system is not responsive enough, and the user will feel less responsiveness from the multiple programs running in parallel in the system. Over here we have a pictorial representation of the same mechanism. As you can see that this process P node is in the running state, and at this point in time we have an interrupt. So the operating system saves the state of this P node into its process control block, including everything that is associated with the process. And then it reloads the state from the PCB1 that is associated with process P1. So over here, when it loads the state, the process 1 will start or continue its execution. So after a while over here, when we have this time slice expired or some other event occurs, then the operating system will again save the state of PCB1 one more time. That is an update on the previous state that was saved earlier for the previous transition. So over here, this updated state of PCB1 will be stored, and then the state of PCB node that we saved earlier in here. So that is again reloaded onto the processor, and P node will continue its execution. So for P node, it may not know that how many processes were running during this time slot, or what has happened in the whole system related to other processes. So one more concept that came across in here is this PCB, the process control block. So we have its detail on the next slide. Over here we have another important concept, that is process control block. Process control block is a block that is associated with every process, and it just reflects all the information associated with the particular process. So it mentions all the states a process is in. It has the program counter, that is the particular counter that holds the address of the next instruction that is going to be executed. Then it has all the values of CPU registers, scheduling information about the operating system. We will discuss about this scheduling in the next module, but scheduling means that which process should be taken out from the ready state and placed in the running state. So all of this information is placed in here as well. Some memory information about the process, what is the limit of the memory, and several other things that I do not want to mention at the moment, because we have a whole section over there. And then how much time is elapsed and how much time is still there, what are the IO devices that are required to for this by this process to complete its execution. So all of this information associated with the process is stored in the process control block. Threads is another interesting concept that one should start gripping from the beginning of this course. We have a whole section of threads and synchronization later in the course, but for now, just take the concept of thread as up till this point in time we have discussed processes that they can execute in a linear fashion. However, it is possible that a process may not execute in one chunk, but there can be multiple course of execution within one process. How I mean this, that if we have one piece of code, so multiple execution strips can work on multiple locations. For example, you can consider it like if we have a thread associated with the IO, it is responsible to execute the code associated with the input and output, while some other thread may execute some other code associated with some other type of tasks. So threads are quite useful when they are implemented in a program, as they can enhance or improve the execution of a process. They are also helpful to synchronize a process with multiple other processes, as well as when we have scheduling and when we have ready and running states. It is possible that for a while one thread may go to perform a certain job while the other one can be in the execution cycle. However, all of it depends on the design options that we select when we are implementing some system. This is a pictorial representation of threads. So you can see we are up till now only familiar with this type of processes, and each process has a code, some data, and some files associated with it. While there are some registers and the stack pointer, I hope you know that stack pointer is a quite important pointer that is used to store the return address of the calling function. So this is quite important if you have multiple functions and you want to store the return address from where you can continue the execution. So this is an overview of a process that is single threaded. However, if we have a multi-threaded process, the code, data and files, they remain the same, while the register and stack, they are independent for each of the each of the thread. So you can see that each thread has its own set of registers as well as stack. So they are a complete set of execution in them. So you can see that a thread can call functions, it can return from them, it can store values in registers, and so a thread is quite useful when we are implementing applications which are which are performing multiple tasks simultaneously. So we can assign multiple threads to multiple section of code or multiple tasks. To signify the concept of threads, over here we have listed several differences between processes and threads. The first one is the processes are resource intensive, so they are heavyweight. On the other hand, threads are lightweight and require quite less number of resources compared to a process. If you want to create a new thread in a process, you require quite a few resources compared to creation of a new child process. The other difference between processes and threads is that switching among multiple processes requires intervention from the operating system. So operating system handles the switching among multiple processes. However, the switching among multiple threads of the same process does not require any intervention or any assistance from the operating system side. The third difference between processes and threads is that when we have multi-processing environment, over there each process has its own memory, all the files and everything associated with it in independent manner. While on the other hand, all threads of a same process, they can share all the resources from that process. So they can share all the files, all the child processes, so everything they can share among each other. Another difference between processes and threads is if one process is blocked for some IO operation, the execution is not possible for this particular process. So the CPU has to schedule some other process even within the allocated time of this process. However, this problem can be solved quite efficiently with the help of threads, where if one thread is blocked and it is waiting for some IO to complete, a second thread can take its time slot, so which is which does not affect the efficiency of the process altogether. In terms of processes, another difference is that every process in a system is independent of each other, so they do not interfere. Usually it's one of the responsibility of operating system to ensure that multiple processes, they do not interfere with each other, unless we have some legitimate mechanism. On the other hand, we have in threads, one thread can communicate with the other with a lot of easier mechanisms that are available. So one thread can read, write, or access the data of the other thread quite easily. The differences that we had on the previous slide reflect one interesting characteristic of threads, and probably that is one of the reasons why threads are so popular, is that in a multi-threaded environment, if we have some IO extensive application, we can associate some thread with it. So if that thread is blocked for the IO request or IO operation, the other can continue their execution, which means that the process will still in the execution state or in the running state while it is also waiting for some IO. So it improves the overall efficiency of a process. The switching among multiple threads, as we had earlier discussed, that context switching is quite a resource consuming operation. So if we do not require to save the whole set of data and files and everything, then definitely that switching can take place at a faster rate. So when we have threads, we have, because we have less amount of data and we have only a few things that we want to save and reload, so this switching among multiple threads of the same process, it is a lot faster compared to switching among processes. These are the reasons why a thread is termed as a lightweight process. However, there are some things that we should keep in mind, that even though we have multiple threads of the same process, at one point in time, only one thread can be in the execution in one CPU or in one processor. So if we have a single processor system, at any point in time there can be only one thread that is in the running state, and other threads, they can be ready state or waiting state, or all the states are possible as we had for processes. Threads have different stacks and registers, and they allow them to operate in independent manner. So by having different stack pointers, they can keep track of the calling functions and the return values, and a sequence, an autonomous sequence on their own, as well as they have a set of registers, so they can store values and they can perform actual operations. So that is why threads provides us a mix of autonomous as well as some independence among multiple threads, as they are sharing multiple stuff with each other. So there are a lot of positive traits or positive characteristics that are associated with threads, and that is why now we are moving more towards multi-threaded applications. When we have multi-threaded applications, we have several issues that we have to face, and various challenges that we have to answer uh, before we can have a successful system. You can see that if we have multi-threaded applications, we can have multiple threads running on the same code, which can cause quite some synchronization problems, and we'll talk about one of them just in a couple of minutes. Then to complicate the scenario, now we have multi-processor systems where along with having multiple threads, we have multiple processors. So now you can see that the whole scenario becomes a lot more complicated. But having both of these things, multi-thread applications as well as multi-processor systems, now it is possible that we may have concurrent processing of one process. So now it is possible that multiple threads of the same process, they can run simultaneously, exact at the same time in different CPUs. So, and that raises a lot of other challenges that we were not aware before. So now we have different interesting problems and their solutions are provided every now and then. One of the problems, and very interesting problem, that is associated with this synchronization thing is critical section. And we will just have a small debate over this critical section just on the next couple of slides. However, we have a whole session on synchronization, and when one whole module is there, when we will have where we will have threads and synchronizations and issues associated with them. So that is there after a couple of modules. But right now we have just a hint or a glimpse of the whole thing, so that the idea is it remains there in your mind. So now we will see what is critical section, and what are the problems, what are the challenges that they can raise, as well as how can we solve them in an efficient manner. So here we have an example of a critical section. As you can see that over here we have one variable that is being incremented, and before this increment and just after this increment we have its values printed out. And then the very same variable is in a multiplication operation, and again before the multiplication operation we have its value printed out, as well as after the multiplication operation. So you can see that this should not be a problem for a single threaded application. However, now let's assume that we have multiple threads running in parallel onto multiprocessor or multiprocessing environment, where we have multiple threads as well as we have multiple processors present in the system. So you can see that it is possible that one thread may start its execution from here. Simultaneously, another thread starts its execution from here. So the one thread is here and it just increments the value, and then it stops over here for some reason, and then the next one moves along onto the next processor. So it prints out the value, it adds it, then prints the value one more time, then prints the value before the multiplication, does this operation, and then prints the value one more time, and probably exits. In the meanwhile, the first thread now prints the value after the increment. So you can see the discrepancy over here that is going to rise, that before the increment the value may be like 1, but after the increment the value will be a 1 increment as well as a multiplication, the result of a multiplication operation as well. So you can see that over here we will have a quite an entirely different value that should not be expected in the usual execution of this program. So you can see that we have different output just based on the arbitrary running of the threads. So this problem is termed as critical section problem. So this critical section problem arises when we have multiple threads executing the same code, and the order of execution can affect the final outcome that you would not get if the particular code ran in a sequential order. So to solve this critical section problem, we have a solution which we termed as mutual exclusion. Means that only one should be accessing this code at any particular time. Mutually exclusive code. So how we deal it, the method is fairly simple, that we have a flag associated with it. So before entering the critical section, we make that flag false, and while it remains false, no one can enter in this section. So after this thread completes its execution of the whole critical section, it can make this thread as true one more time, so that any other thread who wishes to enter this section now can execute it. So this is a very simple way of dealing with it at a programming level. Our operating systems and other applications, they provide some environment, some methods through which this mutual exclusion can be handled in a more efficient way. One such mechanism is semaphores. A semaphore is just a variable and that is used to control the access by multiple processes to a common resource. In an environment where we have this possibility that multiple threads or multiple piece of codes can run in a parallel fashion. So semaphores are variables that control the access of critical section in an environment where we have multiple processes and they have the possibility to get executed in a parallel manner. So they are fairly simple. They provide us quite some interesting and easy implementation of the same concept as we learned onto the previous slides in the form of mutual exclusion. So now let's have a look at an analogy to understand this concept of semaphores in a bit better way. Here we have a simple analogy to give you an overview or deeper understanding how semaphores work. uh, for instance, you have a library that has 10 reading rooms, and the reading rooms are large enough only to accommodate one student at a time. So students can request for a room from the front desk, and once they complete their study, while leaving the library, they can tell the front desk officer that they have left the room. So the front desk officer, they probably uh, they are not using any sophisticated mechanism for this handling of rooms by students, or they do not know which room is occupied or which student is using which room, but they only keep track of the available rooms with a counter, with a number. So the front desk officer just increments that number once a student requests for a room, and the front desk officer decrements the same number once the student leaves the library. So in this way, they may not be aware that who is using which room, but at least they are aware that how many rooms are occupied and how many rooms are vacant at any point in time. So for instance, if that number is 4, they know that 4 rooms are occupied and 6 are still vacant. So in this way, it is a way to provide them an overview of the system without having any sophisticated mechanism. In this analogy, the number that is used by the front desk officer, it represents a semaphore. The rooms represent the resources, while the students who are utilizing these resources, they represent the processes. So students utilizing the rooms will be processes utilizing the resources, and the front desk officer represents the semaphore that keeps track of how many resources are utilized by how many processes. So for instance, in this case, the value of the semaphore by the front desk officer can be initialized by 0, and once a student comes along and requests for a room and that access is granted, then the value of that particular semaphore is incremented to 1, and for the next student it becomes 2, and so on and so forth. So you can see that the front desk officer just keeps track of the number of used rooms. So the basic definition of semaphore is that semaphore is just a variable that provides us a simple mechanism to control the access of multiple processes in an environment where we can have parallel execution of multiple processes simultaneously. So that is all for today, students. I hope that there is no problem in these concepts. If you feel something coming up, please do write to me and we can have some online session. Thank you very much.